and good morning to all of you present. I hope you can hear me. Yes, please. Can you just say yes or no? Can you hear me?
Yes, sir. Yes, sir. You are audible.
Okay, thank you so much. So first of all, I want to thank Dr. Indu, who has invited me to deliver a talk in this international workshop on nanotechnology. I am very much thankful to Dr. Verma, who has just spoken about the applications of the nanotechnology. But before I start my talk, I will just put a small question that really are we proceeding towards a good nanotechnology or a bad nanotechnology? Because why I'm asking, why I'm putting this question before everybody, because as we move to the nanoscale, from bulk to the nanoscale, really is it helpful in some aspects of life, like biotechnology, even in the fertilizers, etc., etc. Right? So it's a big question today. It's a billion-dollar question that are we really approaching towards a good or bad nanotechnology? Right? So thank you once again to all of the organizers. And let me start with my talk with International Workshop on Nanotechnology. So let me have my presentations now. Okay. I hope that you can see my slide. Then just anyone ping me, yes or no, please?
Yes, sir. Yes, sir.
Okay. Thank you so much. So basically, we'll be I'll be talking on this shapes effect on hydrogen response of palladium nanoparticles. So before I start, I want to thank my colleague, Dr. S.K. Hajra, who is with me in working this. And of course, this is entirely a work of my research scholar, Pooja Bhardwaj, who is about to submit her Ph.D. And finally, I want to thank DST for providing funding to conduct this project. Now, we are basically interested for this hydrogen sensor. So why these hydrogen sensors and how it is useful? Now, it is useful for the fire detection. Basically, if it is more than 4%, it is basically we can say that it is basically a hydrogen bomb. Right? So we don't want to have an explosive sort of things, or maybe that we want to have a regulated sort of energy using this hydrogen. So the first application says that why we want to have the hydrogen sensor. First is for the fire detection, because the hydrogen is highly inflammable and become explosive when its concentration exceeds 4%. Very, very important. So this 4% is very, very important to us. Okay. Next is the biomedical. It's basically detectors are used in some specific case studies and new source of energy. Global warming enhances due to excessive use of fossil fuel. So the hydrogen energy is more suitable. For your information, when we talk of satellites, when we talk of space rockets and everything, most of the energy they used to carry, they are basically the hydrogen cells. And of course, for the general safety, it is colorless, odorless, and tasteless flammable gas, which cannot be detected by human sense. That's a very, very big disadvantage of the hydrogen gas. Now, why interested to do this work, and what is the motivation behind this work? So, to exploit these metallic nanoparticles for the sensing applications, what you have, it can be capped by variety of molecular ligands, and we have used as PVP, that is polyvinyl parapolates. So this can be capped off. And why I want to cap it? Because I want to maintain the size. That's the main purpose of capping it. Can vary the shape easily. Okay, this is one of the things, because when I talk of nanotechnology, the surface to volume ratio is very, very important. So I want to have maximum interactive surface. So precisely I want to increase the surface area. That is one of the advantage what we have. Can change the surface to volume ratio. Of course, when we basically cap my nanoparticle with any of the material, in my case it is PVP, that's why I can regulate my shape and hence improves the catalytic activity. Catalytic activity means that it enhances the rate of reaction, but it doesn't take part in the reaction as such. Such activity tuning can lead to development of a good sensor. So sensors means when we talk of sensor, that means it should be able to sense in a very, when we have a ppb or ppm level, right? And in my case, it is practically the hydrogen which is getting sensed by my devices. So in the main contents, what we have is the synthesis of polyvinyl pyrrolidine, that is PVP, capped palladium nanoparticles, and these basically nanoparticle will act as my hydrogen sensor in my device. So we have morphological characterization, and ultimately we'll be ending up with a hydrogen activity of my palladium PVP. So this is just a brief of my synthesis overview. Now we have few parameters that has to be sensed of. One is the synthesis parameter, and next is the sensitizing result basically. And of course, they are mutually dependent on each other. So when we talk of the sensor performance, it can be regulated through the change of shape or size, and of course the interparticle barrier. When we talk of capping the particle, what should be the capping such that the interparticle barrier could be maintained? If my interparticle barriers could be maintained, that means more and more surface area could be seen off by the hydrogen, and it can be sensed properly. And of course, we can have change of shape by using some reducing agent. That is the chemistry part of it. So now the next questions come that why we have chosen palladium. It is catalytic in nature and strong affinity towards hydrogen absorption. It is well known to us for the chemistry people. Converts hydrogen gas, harmful gas, namely carbon monoxide or NOx, into harmless components. It is corrosion resistance, very, very important thing. That means when we make a device, when we sell it to the market, when basically the customer purchases it, with the Indian mentality, it should be a device which should stay longer. Okay, the yield should be longer. That's the main thing. Negligible sensitivity towards air and moisture, easy catalytic activity at room temperature. So any of the device we purchase from the market, it should be quite active even at the room temperature. That's the main thing. Okay, we are not supposed to heat it or cool it or something like that. Easy synthesis and availability. Just now, while introduction, Dr. Verma was telling about this COVID-19, and we have few vaccines in our market, and some of the vaccine basically is stable between 2 to 8 degree, and some of the vaccines are stable at -6 degree. So definitely the peoples are more having affinity towards the vaccine, which have the affinity in the approximately 2 to 8 degree rather than going to the -60 degree. So this is one of the things which we should follow. So easy availability and easy synthesis, that is one of the part that why palladium has been chosen. Now, next is when palladium is exposed to the hydrogen gas, what happens is that you can see the surface of the palladium, it becomes a palladium hydride. And firstly, what happens is that palladium acts with the hydrogen on the surface, and it becomes palladium hydride. And initially, for the information, initially the resistivity increases due to the formation of palladium hydride. And secondly, what happens is that after the formation of the palladium hydride, what happens, the hydrogens start start basically interfering or going inside the palladium, resulting to expansion in volume, resulting to the swelling of the particle. And what happens due to the swelling of the particles? There occurs a something known as geometric effect. So after, what happens is that this palladium particle basically gets swelled. Once it gets swelled, there is an increase in surface area, which exactly help us in the sensing properties. So these effects can be coupled off, basically looking at the gas sensors. So now the synthesis, the exact synthesis of this palladium nanoparticles is by sodium palladium tetrachloride plus PVP plus HCl plus this is my reducing agent, that is ethylene glycol. And we have used the various, this is the method, simply it is heating and stirring at 127 degree plus minus 2 degree for 2 hours. And this is practically the whatever is the parameters we have chosen, that is the optimal parameters we have chosen. And after washing, we get the palladium nanoparticles. This is the percentage of PVP we are using. Although PVP doesn't actually, and nothing to do with the hydrogen sensor, but basically this PVP is acting as a capping agent to my palladium nanoparticles. So we have various percentage of my PVP as 0%, 20%, 32%, 45%, and 60%. And this is the percentage of PVP with respect to my precursor, that is sodium palladium tetrachloride. So now after this palladium nanoparticles has been formed, we went for this XRD, and we can see that it is practically goes with the various peaks, and definitely we confirm that this is a polycrystalline particles. Secondly, you can also see this is 111 peak. Okay, this is 111 peak, which is more intense. 111 peak, this is more intense. We'll talk about this one. And this will help us in identifying the sensor property of my palladium. So this is peak to be matched. So next is the morphological aspect with respect to the change in stabilizers. So this is the important thing what we got in this one. So I have 4 pictures, A, B, C, and D, and this is of course E, and this is the E, that is the 0% PVP. It is practically the normal palladium particles, and you will see the amalgamation and so on. So it is very irregular shape. Okay, so avoiding this E, let me go to this A, B, C, and D. So looking at my morphology, looking at my HR, the same pictures, what we have is that in A, basically it is cubahedron geometry. This is the A, which is this is the particle nature what you have. This is the particle how it looks like. Whereas the B, it is octahedron palladium nanoparticles. This is the octahedron. Similarly for the C, it is decahedron, and the D is the isohedron nanoparticles, right? So these are the 4 shapes we got when we change my PVP from 20, 32, 45, and 60%. This is a very, very important result, and also so we have published this result also, that this shape actually plays in the sensing particle as a sensing mechanism in my hydrogen sensors. This is a very, very important. This is very, very important findings what we have. This is the HR temp result basically. So this you can see 20%, 32%, again 20% PVP and 32% PVP. This is practically what we have. That the shape modulation is occurring by the variation of PVP concentration as well as changing the molecular weight of PVP. So here we have chosen the molecular weight of PVP as 40,000. So this is one of the things what we have, but this is not much important because we are practically looking into the shape of my nanoparticle that is going to able to sense in my hydrogen sensors. Finally, we went for the device fabrications, and this is very simple device fabrication. This is just the, what we say, it is just a silver lining. This is, you can see over here, the palladium nanoparticles, and just we have connected the digital multimeter, and we have just a film on my glass surface, and this is practically the silver film or the silver paste we can have, and this is the response time. This is a very simple experiment we have done, and anybody can do in his lab only simple a BTech or a BSc lab. So the hydrogen interaction with respect to the change in stabilization we can see, and of course the change in PVP molecular weight. Recently I have shown of the 40,000 molecular weight of the PVP. Now here we can see that what happens is that if you look at, let me see this, the zoom nature of that one. So initially what happened there is, this is the time and this is the resistance. So initially there is an increase in resistance. I hope you remember that when the hydrogen initially act with my palladium, a palladium hydride is formed, and which practically is responsible for the low conductivity or increase in the resistivity. And after that what happens, so this part is termed as practically the electronic response. And after that what happened, there is I told you that there is a swelling of nanoparticles as the hydrogen get absorbed by the particles, and ultimately what happens is that the resistance drastically drops, and this is termed as the geometric effect. And after that you put off the hydrogen. As you put off the hydrogen, again there is a recovery. Okay, so this is the main sensor. This is the main sensor characteristic what we got in our sensor devices. So this is we have done with a 32% at 40,000 molecular weight of my PVP, and this is the 20% at 40,000 molecular weight of my PVP. So this is the response time what we can see according to the different particles, different shape of the particles, right? So we can see over here that at different particles, that is at 15%, 32%, that is 45 and 60%. So we can see over here the best response time over here. It is at 100 ppm of the hydrogen. So we can see over here that this is for the 15, this is for the 32, and this is for the 45 and ultimately 60. So we can see over here that this is at room temperature. Of course, we can see over here that whatever is the best we can do, or whatever the response time we can see at my 100 ppm. We have done the same experiment at 50 degrees centigrade also, but you can see over here the response is not good. The response is not good. So this is the general, then we went for exactly to find what exactly is happening. So when we talk of the general hydrogen sensing mechanism, what we say is that in absence of hydrogen, it forms the hydride, what I can tell you, and ultimately there is a swelling in my palladium nanoparticles, and ultimately you can see over here there is a swelling, and ultimately what happens is that there is a volume expansion, and my surface to volume ratio get increased, resulting to a better sensing mechanism. Of course, initially it was electronic effect followed by the geometric effect. So now we have already seen through these various figures, that why my octahedron or at the value of PVP at 32% is more effective, because while looking at the octahedron surface, we can find that the surface to volume ratio is more, that is 1.156, followed by decahedron, that is at 45% of PVP at 1.139. But definitely this 32% plays an important role, very, very important role, because as my surface to volume ratio is maximum at this point, so the sensor part at 32% PVP is maximum. So we have done the XRD, and we have just compared with this XRD, and you can see over here that at 32% PVP at 111 surface, because this 111 surface is the dominant facet in all of this one. So in case of regular octahedron, we have seen that 111 facet plays an important role and resulting to, as we have seen earlier in case of XRD also, this 111 facet plays a very important role as the intensity high, and this facet is responsible for sensing the hydrogen. Finally, with respect to the morphology, for PVP having 8,000 molecular weight and with nanoparticle surface to volume ratio, maximizes for 32 to 45%, but definitely this 32% is a better, that is octahedron to decahedron. Also from facet study, the dominance of 111 facet is observed with the increase in PVP concentration. And the change in morphology is also observed from 40,000 PVP molecular weight. So with respect to the hydrogen sensing, the isolation of electronic effect and geometric effect with a variation of concentration of PVP having the molecular weight of 40,000, exactly once we say it is 40,000, we are still working on it to optimize this result, but definitely the 32% is the best in our case. So the manifestation of both, that is electronic effect and the geometrical effect with the variation of concentration of PVP having the molecular of 8,000. Also a response optimum is observed PVP in the range of 0.32 to 0.45. But as I told earlier, that 0.32 or 32% of PVP gives the better result. We have also done with some of the strain, that is practically the stability, and we have seen that our device is quite stable, okay, and before and after the hydrogen exposure. So this is practically a good results, but we are still working on it, and that's all from my side. So the conclusion is that 32 to 40%, 45% PVP quantity is an optimum concentration range for the hydrogen sensor. I should say that this is just with respect to the present study, we are working on it, and the octahedron shape of particles, and also not only octahedron shape, but also the 111 facet also plays an important role at 32% PVP palladium, and since it acquires a high surface to volume ratio. Decahedron palladium nanosensor shows minimum response time due to the dominance of most active and densely packed 111 facet, and higher molecular weight PVP is able to isolate the electronic and the geometric effect. Practically, we are interested for the geometric, more of geometric effect rather than the electronic effect. So thank you so much. I'm open for the question. You can just you can have. Thank you so much. You can have.
Thank you, Professor Barman. Professor Barman has highlighted on the topic of shape effect of hydrogen response of palladium nanoparticles. He had talked about the hydrogen sensor, how it can be used in fire detection, biomedical, and general safety. He has also concluded that 32 to 45% of PVP quantity is optimum. Thank you, Professor Barman.
Thank you so much, sir. Thank you so much.
Thank you. Now, I would like to introduce Professor V.C. Chauhan. Professor V.C. Chauhan is a professor and dean and head of, in School of Physics and Material Sciences in Central University, Himachal Pradesh. He is Ph.D. in neutrino physics from HP University. His area of interest are low energy solar neutrinos, neutrino oscillation, holography, geothermal energy, history, and philosophy of science. He is a postdoctoral fellow from Technical University, Lisbon. He has a teaching experience of 23 years. He was the chief guest and guest of honor in several institutional and social functions and programs with wide media coverage, a resource person in several educational training programs. He is a visiting associateship by Inter-University Center for Astronomy and Astrophysics, Pune, since August 2010. He is on the editorial board of Journal of Nuclear Physics, Material Science, Radiation and Applications, Journal of Geology and Geography, Oriental Journal of Physical Sciences. He has many awards to his credit. He is member of Board of Studies, Department of Physics and Astronomical Sciences, Central University, Himachal Pradesh. He is associated with the Advisory Director, Higher Educational, as a Higher Education by Government of Himachal Pradesh for a program on nuclear science and technology. He is associated with Bharat Shiksha Ratan. He has been awarded Bharat Shiksha Ratan Award 2012 by Global Society for Health Education and Educational Growth in New Delhi. He is a visiting associateship of Inter-University Center for Astronomy and Astrophysics, IUCAA, up to July 2013. So I welcome Professor V.C. Chauhan to give his address.
जी नमस्कार.
नमस्कार.
Namaste सभी को और it's really a great pleasure for me to be introduced and to be involved in this online conference, online workshop on advancements in nanomaterials with futuristic engineering applications. Am I audible, sir? Am I audible?
Yes, sir.
Hello.
Yes, sir.
Hello. Hello.
Yes, sir.
Okay, fine.
Yes, sir, you are audible.
Okay, fine. So, which is being conducted by Career Point University, Department of Physics and Department of Mechanical Engineering. I'm really grateful and thankful to the Honorable Vice Chancellor of the University, Professor K.S. Verma, and Professor M.R. Sharma ji, and Dr. Indu Sharma, who is continuously in touch with me for the last 1 month or so, and giving me a chance to interact with you for this during this workshop. I wish all success of this event, international level, and given the audience, I have my research interest has been already discussed, and given the audience, I have simplified my talk, made it less technical to the audience, so that it will be understandable to all of you, and maybe there may be some questions, so that we can take after this lecture. So I'll be sharing the screen, and I hope it will work, and you will let me know. Is this visible, sir?
Yes, sir. It is visible, sir.
Okay, fine. Thank you. So my talk, I'll be talking about the tiny, because this this workshop is on advancement of nanomaterials and futuristic engineering applications. Definitely, I'll be talking about materials also. I mean, only about materials, but a little bit deeper than the level you are talking. So it will give a different dimension to the participants of matter, that how it constitutes everything in the universe, and starting from the tiny level to the magnificent, this vast, magnificent universe. So I'll be talking about that part, and I hope it will be enjoyable to you. And so let me start with that. These are my interests, as already dictated by Professor M.R. Sharma. I talk about astroparticle physics, neutrinos, dark matter in the universe. that is something very interesting field nowadays, and the matter is dark about in the universe. I'm coming to that slide also, and most of the matter, the universe is dark. So it's very interesting for all of us to know about. And philosophy of science, history of science, energy studies, and geophysics, these are my interests. So okay, anyway, so this is what I'm talking about. So the overview of my lecture will be something like this: big and small. So starting from small to the big level of galaxies and clusters, starting from the strings and particles much smaller than the nanoparticles, and standard model of those particles, a periodic table of those particles, their interactions. Then neutrinos, I'll be talking about a little bit about that also, because that will be something new to all of you, and it would be interesting to know about. Dark matter, as I said, and then open questions. There are several open questions in the field, and then my conclusions will come to that. So you will see that the universe, because we are living in here and we are doing conference on nanomaterials and this workshop on nanomaterials and their advancement, futuristic engineering, we are doing about all that things, and we are having this online conference, and we are having all dynamism in the universe. But only let us ask this question, that why that could have been possible, that we are here and we are able to ask such questions. We are able to organize such conferences. We are able to think about those kind of things, and we are able to the science be born in such a world where the science has developed to this level. So this is something much deeper question and philosophical question, and of course it is a little bit along with science, and it is a little bit anthropological also. So the dawn of universe, dawn of time, it starts from where it starts to when the time starts. So we believe in science, in cosmology, that there is some dawn of time at some point of time that in history of universe, this all and everything started from a big bang that we call about, that we are more convinced today that there was some sort of that kind of bang kind of thing, and then all and everything created out of that. Although it looks very funny thing, and how something can start from a bang. So, but this is reality that so today's scientists people are much more convinced about this thing, and we believe on that. So we have several evidences also, of course, several questions, of course, being opened there. So our universe is today is supposed to be 13.7 billion years old, and we are here. And if I am to talk about the size of the man and the size of the universe that we know, starting from the microparticle, for example, 10⁻⁻15, that is meter, that is femtometer, that is the size of the nucleus, or even smaller than the nucleus of hydrogen atom, that is starting from the you can say the nanoparticle size, from starting from that to the size, the man is standing there, and you will see this is the size of man. And you will see up there in the picture also, there are this size is mentioned over there, and then you will see the size of stars again and galaxies up to 10 to the power 24 meters. So this is the thing that we know about today, from starting from the micro to micro level to this magnificent world. So please stop me if you are unable to understand, or you are unable to see something. Maybe you can call, the organizer may call me on my phone, so that if there is not visibility, there is any problem, so I would be able. So you will see this is it appeared in magazine, so I got it from there. So it is Earth is being seen from the vicinity of Saturn. flat things on this dot. Even if you go to the scale of the universe, then we are even not even the dot. So let us take a journey into the deep into the space that you will see that we are a part of a big galaxy, a spiral galaxy that is called Milky Way. So it rotates, and we are somewhere here. The sun is mentioned over there. So we are somewhere here, and the solar system is there. And some relevant distance units are there. There is one unit that we use to use in the large scale structure, that is light year and parsec, an astronomical unit for distance. So these two units, first one are for the time, measurement of time in large scale. So light year means it is the distance. It is not the time. It is distance basically, and it is a distance traveled by light in 1 year. So it's very big, huge distance. So for measurement. So these all are distance units. I'm sorry. So 1 parsec is 3.26 light years. So these are the measurements, because we need to go to that level, scale level, to understand all these things. And so if you see go a little bit deeper, then you will see that we are somewhere here. The sun is mentioned over there, sun location. And the Milky Way, in the Milky Way, it's beyond even that part. So you will see there are several stars in the Milky Way. This type of situation. So then coming to the next, and you will see the Milky Way a little bit smaller, and we are going deeper into deeper, and the universe is so big. And then you are here. You will see just that part. So your Milky Way is just now going to be like kind of a dot. So you will see this Milky Way even disappeared from the screen. So you will see all of the clusters of the galaxies. This is our situation. So you will this kind of, if we are a scientist, so we should it makes us also to think about our purpose of life. Such a magnificent universe. We are not even in dot. Our place is not even in dot, not even a dust particle. So still we are, of course we are. We should think big and good, but not bad at least. So why we should not this fighting and everything? Why we are always struggling for making pain to others. So if you see this is our situation in the universe. Even dot galaxies like a dot. So here, everything is disappeared, even that clusters and Virgo, we are a part of the Virgo cluster. You see that we are here, and everything disappeared. This is the situation. So 50 megaparsec is the dimension mentioned over there. So how big is everything? In this slide, you will see that we are totally lost in this huge gigantic universe. So this is our picture, and big and vast, and we are nowhere. We are now here, or we are nowhere. This is the situation, and this is believed that the universe was created some sort of this kind of stuff. Big Bang happened, and something happened in there. Then with time we are going this way, towards right hand side, and then you will see some particles, small particles, big particles, and then outside you will see the galaxies are there, stars and galaxies and everything. Because we are a part of solar system. So solar system is a part of Milky Way. So Milky Way is part of some bigger part. So everything is is made up of these small particles. So again, this is another picture of the history of universe. You will see understand the origin of the universe. We use high energy physics tools. So in high energy physics, we talk about, when we talk about deeper into the universe or deeper into the matter, then you will be entering into a very high energy zone. You need to enter into very high energy zone of energies for observation. You need to to see something smaller and smaller. You need to have a very powerful instrument that is to be having more high energy. Should be high energy. High energy means the wavelength will be very small. So very small wavelength can interact with that small particle. So then as a result that we will be able to see that particle. So this is the way, and high energy physics is a field. We talk about these all dimensions. On the cosmology, you will see the large scale and very deep, small scale. They seem to be connected. It's like a snake eating its, the tail. So you will see this micro level matter, how it goes from diamond level to then second level, and then you talk about these kind of particles, nanoparticles and all, and then you go deeper and deeper. Ultimately, atom there, and then atom, there inside the atom there is nucleus, and all inside the nucleus there are three dots there. These are called quarks. In a nucleon, for example, neutron or proton, there are three quarks. And inside the quarks, these quarks, there seems to be some kind of loops, not not only the particles, but the loops. These loops are called string particles. That's a string theory is there mentioned about that. They're smaller, inside those smallest particles, they are, the strings are there. So that's one of the popular theories so far we are dealing with. And we are, of course, still a long way to go to finalize this thing. So we can see the understanding how the universe, God creates this all and everything. If we believe in God or whatever, some order, highest order, which has created, because something who has designed this universe, everything so beautiful. So there must be some designer, and then designer you can call God, or you can call something else. So that is the highest order I am talking about. How he created this everything, so beautiful. That's a big question. So now I'm going to the deeper and deeper into matter. And now earlier I was going deeper into the universe. Now I'm going to deeper into the matter. You will see that an apple. If it's a general question to you that if you cut an apple size object, or an apple, for example, how much times you will cut it down and down and down, reaching to the level of atoms? That's a very beautiful question, and I've seen that. Going to the nano scale. So how much times you need to cut that? So if you take a knife, then cut it down, and it's a question that to the level of nanometer scale. So the answer for this is very beautiful, that you need to cut 84 times. So it's very interesting question and interesting answer to this thing. And so I'm going to the next slide, and then you will see how this apple is going down. And if you cut it down, it goes to the level of strings again. Quarks again, these quarks and neutron, proton, and everything. Ultimately, you are going to that level. Of course, technological level, you are stopping yourself at the nano scale, and you are doing some wonderful things for the welfare of humanity. So these all things, there's early particle physics and discoveries and nucleus and tiny everything. I don't need to repeat these things. So in chemistry, you are familiar with this periodic table kind of thing, and however, in particle physics, we have also that kind of stuff. Periodic table, I'm coming to that. So this is some sort of nucleus. It constitutes proton and neutron. This sort of thing is there. Nucleus, how nucleons are, and that's what I was talking about to you that earlier also. So if you go from size of atom, go down to the level of quarks, how many times you need to cut it or divide it? So you'll see this is some sort of so small in size. 10 to the power 18 minus 18 is the size of electron and quarks, to the level of 1 nanometer, or 10 to the minus 10 centimeter meter, sorry. So these are the quarks, and this color charge there. These things are a little bit technical. I'm not going to detail of that. Inside the quarks, there could be some. There are some. In the families of quarks, you will see there are there are up and down, and there are 6 quarks that we are familiar with so far. And this is what is current understanding. So you might have heard about this large hadron collider and God particle, this kind of stuff, and people doing big, colliders, developing big colliders all over the world, like for example in CERN, Geneva. So that's a big question, beautiful question to ask, that why you need to collide this particle or antiparticle or small particles together, so small particles together, and creating some huge amount of energy. So that's again, the answer is again going back in time. So it leads you to back in time of the creation of the universe, because we believe in Big Bang theory. So we believe that very back in time there was high energy. So particle at the Big Bang, for example, there was huge amount of energy was there, and the temperature was very high. So far we know that at that level, and that's what we need to go to back in time. Go to the collider of the particles to see that energy. So this is a particle Jew kind of thing, and then anti-particle. There is another concept also that we are familiar with, that the particle, they are there, but also universe created anti-particles also at the same time. Were created in the universe, and then there must be some anti-electron, anti-particles, and anti-atoms also. But there's again a big question that where that antimatter has gone, because today we see only matter around us. So otherwise we would have been even existed if there would have been the antiparticle nearby. So somehow this antimatter disappeared somewhere, and that's why we are here, and we are we have not, fortunately not collapsed, and we are here to doing all this stuff. So coming about the periodic table of particle physics, that is called standard model. We call that standard model. That's a sort of periodic table, meaning some sort of arrangement of the particle of these particles in a table, as you do in periodic table. So you will see this is a very interesting model so far. It has fetched 32 Nobel Prizes. That's a very big question, big, good to know, and very big question that how it happened to be so. So this is a very interesting thing, and this has a promising future so far, because still this model is, people are working more and more about it, and going even beyond that. This model does not cover everything, reality in the basic understanding of matter or science. So you will see that there are matter, forces, and everything there. So this is a periodic table basically of matter, particles, and this is some sort of periodic table. And then we will see that there is standard model, and this again, these are the column different forces. 4 forces are there in nature. So you will see gravity is not included here. These are the scales of these forces, because since you are doing this all kind of nanoparticle stuff, so you are dealing with the electromagnetic force only, and not weak force, not strong force, because you are not entering into that much deeper that level. So you are already dealing with all in this force, electromagnetic force, photons and everything, and that's the thing. And 4 forces, as I talked, that are strong, electromagnetic, weak, and gravity. So how these particles are involved in doing all this stuff. So the 4 forces, again, there are different particles which are transporting these forces. They have been identified and even proposed. Some new which are not so far identified. There are some, for example, gravitone, and mostly the gravitone. However, we know photon, we know even those other particles also. It's these W bosons, weak force particles. We know them. We have seen observed them. So this is again the same question, and the answer, the question is, why these particles, these force carrier particles are involved there? Because they are actually gluing this world, because basic fundamental particles are basically the electrons, the quarks and leptons. In quarks, even these up and down quarks, and then electrons. That's it. So these are the fundamental particles which constitute everything in the universe. But these are the building blocks. like bricks and stones of this entire gigantic inverse structure. So these glues, these are the basically cementing, doing the cementing work. These force carrier particles. These are that's why I call them glue. So boson, photons, they are all glues. They are fixing this structure and making this making us to stand. So we are हम अगर खड़े हैं अगर if we are doing this all kind of things, so we are only because of this glue. अगर if there were no such glue in nature, so we would have not been there. So these are very interesting things which we should which opens quite possibilities for us to work on more. Understand the basic understanding, understand the basic structure of this entire creation. So these are the masses. If I am to talk about mass is GeV over C square, right? Is the unit of mass in high energy scale. So you will see that 80 GeV, 91 GeV, something like that. So if I am to talk about again the masses, so particle masses are going like this. These are in the y-axis. There is mass in GeV, and then you will see how these masses goes up from this potential minus 3 to around 3 to GeV2, and this scale tends to about 100 something, 170. Top quark is 170 GeV, something like that. So these are the masses which has been observed in the laboratories. If I am to talk about the standard model particles masses like these quarks and leptons in this kind of block to show, then you will see it like it will go like this. These are again seen like this. These masses are seen. This highest is the top quark. T stand for top quark, having very highest, 170, around 170 GeV mass. So there is an interesting thing which I want to share with you, that you might be having question that how there was big media coverage in there all around 7-8 years back about God particle, that kind of concept. So this was discovered in CERN in Geneva laboratory, again in the collider of proton beams, and those were collided, and a huge amount of energy was created, which was there in the which supposed to be there in the Big Bang time, and that particle also created, which is having a very important role in this gluing and in this even in the mass, even in the building of this entire universe. So that is called Higgs particle. That is also called quartz particle. That is also called Higgs boson particle. So that is basically shown in these three pictures, that somebody is coming. If you are standing, somebody, there's people, thousands of people in the hall, and somebody, eminent personality, is coming from outside, from political leader or some scientist like Einstein, entering in the room, and then you will see how he's being surrounded by. So this is happening with that particle when it interacts with the fundamental particle, the elementary particles. Then it gives some weight to those particles. It gives some energy to those particles, and that's a little bit deeper concept. I'm not going to detail of that, because that will need some more time and some little bit background also. So this is the way how it interacts. The Higgs particle, God's particle, Higgs boson particle interacts with other particles, mass giving. So this is a view of CERN laboratory in Geneva. You need the huge I'm just putting it here because just to show that to see smallest and smallest particles, small and small particles, you need a big and big eye. That's very interesting thing to see small and small particle. You need big and big eyes. You need more and more energy, in other words. So it's a very big. You can understand that it's having 17 mile circumference. About 4,000 scientists are involved in this project. Huge money is involved and everything. So if I am to talk about the energy budget, as I was talking about the dark matter part. So dark matter part, the universe you will see is about 95% dark. Out of which 73% is dark energy and 23% is dark matter. So matter and energy, they are all together leading to 96%. About 96% of matter of the universe is dark. So meaning that what we see around is in the night you will see the stars and everything. Whatever you see around, daytime also, in the light on Earth, for example. This is just a 4% of this entire universe. So this is very interesting thing. And 95-6% around the matter, the universe is dark. And out of that, I'll be talking about is 23%, and that is dark matter. So neutrinos, if I'm to talk about that part also, neutrino is just having very small component, that is 0.1 to 2%. But this is very small particle, very small mass. So, but it's its abundance is so large, like next to photon in the universe. So it's having so much abundance in the universe. So about 63, you will see just 63 billion neutrons crossing per centimeter square per second, meaning that through the nail of your thumb, 66 billion neutrinos are crossing in 1 second. So this is again, unimaginable thing. So where do we find these neutrinos and dark matter? These are the various sources. So since time is limited, so I will be just speeding up the slides. So this is a neutrino particle showing these wigglings there. So these oscillates. This has been observed that this particle oscillates. And there are certain oscillation for this particle. This has been recently observed, and if the oscillations are there, then we see that this particle is having mass. This is not massless. So in the standard model, I was talking about that periodic table of particle physics. That in there, neutron is assumed to be massless, but ultimately it is massive. So we need to go beyond the standard model now. So it leads you to the physics beyond standard model. So these are some data feeds which which has been recently corroborated by various surveys and studies. So this is one thing. Another thing, I was a little bit talking about dark universe, so dark matter and everything. So how dark matter was observed and discovery of dark matter has been discovered through. There are several evidences for dark matter to exist, which shows that dark matter is there in the universe, and that is by percentage of around 3% of the total composition. Strong lensing, hot gas clusters, bullet clusters, supernovae, CMB stand for cosmic microwave background radiation. These are several evidences. For example, the biggest popular one is the rotation curve of the galaxies. The spiral galaxy rotates, so it rotates. Its rotation has been seen so like it's going flat at a far of distance. Also, if you go thousands of light years from the center, you will see that there is a flat curve, and that flat curve leads you to some matter which is unseen matter, which could be tiny as well as unseen. So that is unseen because we can't see that, and that only interact with the rest matter by the gravitational force. Not any other interactions are there. So this is a big question that people are working on. So this, as I also talked to you about the neutrino, there is a sterile component also of that neutrino. Sterile means less interacting again. So less interacting leads it to make it a very promising candidate for this dark matter. So people are working on that this could be warm dark matter, cold dark matter, hot dark matter. These kind of possibilities are there. What are cold dark matter, hot dark matter? This is another question. So then other dark matter candidates, there are several other dark matter candidates also, like you'll see that Q balls and cold planets, comet-like frozen hydrogen, and black holes and everything. They are also supposed to be the possible candidates for dark matter. So since time is limited, so I am just wanted to conclude, and maybe we can take some questions if you have any question, or we can take question off the time of the session also. So the big questions that about these tiny dots tiny particles are mysterious particles, for example, neutrinos having several open questions, and the universe is mostly dark, and neutrinos plays a great role in the construction or in the constitution of this dark matter, unseen matter. So great potential of research, of course. Then this is an interesting thing which I want to share with you. That is the verse which has been written by Professor Stephen Hawking. You know him. You must be knowing him because he's a very popular man next to Einstein of the modern time. He can be called Einstein of modern time. And he wrote that construction of the nature points us to a purposeful designer. That's I was talking about God. the cause of space-time dimension must be outside the space-time dimension. So I mean the cause is somewhere else. So it's not only the cause itself, it's somewhere else. So it is pointing out some some force outside, a greater, larger order that the people also call theist people call God. All the subatomic particles. This is from a Cosmic Dance of Shiva. This is from some book I have taken. All the subatomic particles in the universe arise from some different vibrating frequencies. Universe in symphony-like violins, playing different notes. Music is at the very base of space, time, and matter. It's a very interesting thing that we see around. Whatever we see around, we are doing nanoparticle workshop, and we are doing, engineering. We are doing so many other things, politics and everything. We are enjoying life. This all and everything is just is a creation. This creation, multi-dimensional creation, is some sort of a music, is some sort of a violin, symphony-like violin, playing different notes at different notes, and of what? Of the particles. Basically, this is a dance of the particles. This is the tiny dots, the tiny and unseen particles. So music is at the very base of the space-time. Whatever we see, space, time, and matter, all and everything. Their music is basically the very base. So I'm adding this of Lord Shiva, the Nataraja that you see in your drawing rooms also, or I've seen interestingly in laboratory. I was talking about in Southern Geneva when I went to there in 2004 or 5. So this is what it depicts. It's basically the Tandav Nritya of Lord Shiva, Shiva's cosmic dance. It's basically a dance of particles. That's it. And everything is mentioned in there, that what the dance of Shiva depicts. So this is a picture when I traveled to when I visited their laboratory in 2004 August. So this is instituted at the very main campus of this laboratory, Grand Laboratory, Large Hadron Collider, CERN in Geneva, and Physics Laboratory, International European Physics Laboratory. There, this has been instituted, this Nataraja of this very big size. And interestingly, on this metal plate over there, you see there in the left-hand side, it is inscribed the wordings of Professor Carl Sagan. He's a British cosmologist and of the level of Professor Stephen Hawking. He mentioned this. This has been engraved on this metal plate. That Vedic cosmology. It points us to this Lord. The dance of Lord Shiva is nothing but a dance. Is a cosmic dance of the particles. इसे very इसलिए इसको हम लोग ऋषि लोग हम लोग जो है इसको दिव्य नृत्य भी बोलते हैं. So Davic, it's beyond explanation. The dance beyond explanation. Vedic cosmology is the only one of which time scales corresponds to those of modern scientific cosmology. Vedic cosmology is yet another ancient Vedic science which can be confirmed by modern scientific findings. The cosmology of the Vedas closely parallel modern scientific findings. It's very interesting and encouraging, words for us all, and how our rishis they experienced this kind of thing about the mysteries of nature. So these are my point. This is my email ID and phone number. We can have question answering also of the class and any time. So thank you very much for your kind attention, and I'll be welcoming the question if any. Thank you very much, organizers, again, and that's it. Thank you very much.
Thank you, Professor Chauhan. Professor Chauhan has talked about the tiny and unseen matter. He has talked about the neutrino, the dark matter, the Big Bang theory, and how big is the universe. We are not even a dot in this universe. The universe is big and vast. He has discussed how has this universe been designed and how small is the matter. He has highlighted the quarks theory. He has also talked about the antimatter, then the standard model, in which how the scientists are working on the standard model. 32 Nobel Prizes have so far been given on the standard model. There is a strong nuclear force, the glue, which is operating in this world. He has highlighted the Higgs boson particle, the God particle. Then there is, in the universe, there is 23% dark matter, 73% is the dark energy, and only 4% is the ordinary matter. So he has highlighted the cosmic dance of Lord Shiva, that is the dance of the particles. And he has also mentioned that the music is the very base of all space, time, and matter. He has highlighted the Vedic cosmology, and it is written in our scriptures that the music is the very base of all creation. That is called the Sabd in somewhere, or in some scripture it is written as Nad. So thank you, Professor Chauhan. Anybody, if anybody has some query, he can raise his question. If you have any query, then you can interact with him on his email. And thank you, Professor Pran. Thank you.
You're welcome. Thank you, Dhanyawad.
Thank you. The next speaker is Dr. Khalid Majasim Batu. Professor Khalid Batu received his Ph.D. in Applied Physics from Department of Applied Physics, Zakir Hussain College of Engineering and Technology, Aligarh, Muslim University, Aligarh, India. He is currently an associate professor at the King Abdullah Institute of Nanotechnology, King Saudi University, Riyadh. He has got many awards. Outstanding Scientist in Nanotechnology 2017 award. Professor Khalid Batu has authored more than 90 papers in peer-reviewed journals and conferences. As principal investigator, he has in his credit a number of his projects of interest, national repute, from National Plan for Science and Technology and King Abdul Aziz City for Science and Technology, Kingdom of Saudi Arabia. His international academic comprises of Academic Excellence Award from Dover Publication, New York, 1998. He is also the recipient of Young Faculty Award 2016 by Venus International Research Foundation. He also received a Speaker Award at King Plastic Summit 2017, Riyadh, Saudi Arabia. So I welcome Professor Khalid Majasim for his talk.
Good morning, all of you, and I'm pleased that I've been given a chance that I may be also one of the speakers to this important webinar. It's very unfortunate that we are right now dealing with the COVID-19 and we are unable to meet face to face where we can discuss practical grounds of science, the future and the challenges. But anyway, I hope that this unfortunate time will also pass, and soon we may get rid of it, and things may restore, and we may start a new life again. So here I'm going to present my talk. Are my slides visible?
Yes, sir. It is visible, sir.
Okay. I'm going to talk about ceramic oxides. Ceramic oxides are somewhere the mostly discussed materials. They are surrounding us almost in every form, and the most two important aspects of ceramics are multi-feroic materials and magnetic properties. There are other properties like they are dilute magnetic semiconductors, they are supermagnetic or any other forms. So I may try to combine them within the two forms. I'm not going to talk about insulating properties. I'm not going to talk about other properties. I'm just trying to concentrate here only in two properties: ferroelectric or multiferroic or magnetic properties. So I'm just giving a brief introduction about where from we are coming when it's about oxides. It's more than 60 years that semiconductors were discovered, and we got these semiconductors in the form of PN junctions. Then from the PN junctions we had a transition. We went to NPN or PNP transistors, then to IC technology, and later it was 1986 when the first Nobel Prize came to the Kemmerlingam on when he discovered high temperature superconductor materials. Now initially, when we were talking about oxide materials, or ceramic oxides you may call it, which are mostly residing in the D block elements of the periodic table, we were talking individual atoms. We were talking about iron, we were talking about manganese, copper, or zinc. They were just discussed individually, the individual property of these materials. Later on, what we did, we just tried to combine the materials, and they came as shoulder to shoulder, they came as layer to layer, and they changed the properties of the materials, and we came up with the fascinating properties as multi-layers, as paramagnetic materials, as antiferromagnetic superconductors, ferroelectric, multiferroic, and various kinds of geometric frustrations, spins, pinning effects, and they all were when the atoms, when the oxides came shoulder to shoulder, or they came face to face, and we had a different way to look into the properties of ceramic oxides. So one of the important histories of the computers, if you go back in 1940s or early 50s, you can see that this was earlier computer of where the people, almost 20,000 in number, were working to just to make certain calculations, whether it was plus minus, whether it was multiplication or division. They used to have these vacuum tubes, and you can see how big the size of the vacuum tube was. The ladies there, they were just programming. They were just there to program. How they were programming? They were just using the manual system to plug in and plug out. And the middle, you can see the man here replacing a bad tube. So it was a very hectic. A lot of manpower was used and a lot of space was used. But as we saw, the progress of going in semiconductors, what we saw that there was a huge transition from a huge space occupation to a minimum space being occupied. So you can see in this IBM 7094, they were just manually doing the calculations. The only good thing what happened that it was just by default, they used to have the punch, which you can see in the ribbon here, which was a printer. In the middle is you can see the printer, and in the corner you can see the printed information. That printed information was, the punch was where the hole is, it was considered as a 0, while as there is no hole, it was considered as a 1. So binary language of 0 and 1 of the computer, it just started by default. So the same language was carried out when we started using these algorithmic or the tubes being replaced by semiconductor devices or IC technology later on. So a transition of bigger space, a transition from large number of people being used in the calculation of ENIAC rather than a computer then got replaced into a small box of computer. Then we have the laptop, iPad and iPhone nowadays. So how it was actually working, this is the memory I'm just showing you. This was the core of the memory in 1960 until it was replaced by semiconductor memory later on. So 1 megabit chip, you can see how big the size was in 1989, and now you can see 16 GB single DDR4, which is now being right now in computer memories, working very fast. And where it is going, the growth of data versus growth of the data analysis. If you can see from early 1995, I'm not going to backwards because then it's going to be a huge lagging of the data. Somewhere between 1995 till 2015, you can say that we were just on a same platform where there was no much bigger gap between the data available and the data accumulation. Reason being that we were not too digital. Now it has started almost in every country, be it India, the large population, where the largest population is, whether it is India, whether it's China, Pakistan, Bangladesh, or any other country having a huge number of people, they have started getting digital. So as they are getting digital, the human information is being stored into computers. We are having a huge growth of the data. As the growth of the data is getting bigger and bigger, we are in requirement of bigger spaces so that this data can be stored. What we have done so far, we have, as if you look into the 4 aspects of the computer technology or IT technology, we have worked into storage, we have worked into networking, we have worked in CPU, we have worked into the bandwidth. As if you see into the storage, we have got, as per the economical size, the storage is increasing, but the prices are decreasing. That's a good achievement. Same, in a similar way, we can see we have increased into a networking. We are hosting much and much size networking. We have gone to from early networking where we used to use the wire. Now we are using a better connectivity through quantum computing. We are trying, in fact, to quantum computing into quantum networking in 2020. Now, if you look at the CPU, the same CPU size is decreasing and the cost has decreased, bandwidth has increased. So when we talk about bandwidth, so we are talking about the 6G configuration, which China has launched, and 5G, which other countries are working already or are working. So looking into this aspect, there is one important thing. That's the More somewhere said that as the technology, as the time will progress, we need the double every year. The chip size, single chips will double in the number. So they will be in millions and millions required. However, it was Jensen Huang, CEO of NVIDIA, which claimed in 2019 that Moore's law has died. It is no more a gap between available data or available information and available storage capacity or available computer or whatever the processes we have. So we are almost there. However, we saw that earlier we used to have number of logic cores. They were in millions, if you are talking about. So we in the graph you see a typical power about how much it increased frequency, how much it was. So it started increasing. The population of the world has increased as was required, corresponding. The transistors are the IC technology in incorporating this information or embedding this information on those kits. But it is becoming almost difficult as semiconductors we are working. No doubt the manufacturing is shrinking, the components are shrinking, the sizes are shrinking with the use of nanotechnology, where if you see in the iPhone 12 category, we are using the bionic chip of 7 nanometer. So the processor is very, very good. You may try to open as many applications as there you want. It's not hanging. And personal experience, I have saw it. It's not hanging. Although we have worked very tirelessly, we have achieved this greatly. The size has been reduced, but to adjust to this size, we require a battery space. The battery of the phone is not that much, so the energy consumption is very high. At the same time, we see the cost is getting very big. So that is those are the issues which need to have the right attention in order to deal with. Intel Core founder, if we go to Intel Core founder, where Gordon Moore in 1965 actually, who predicted it, that how we are going to have the requirement of the chips. Now, if you see from earlier stage of 1970s, where the transistors started working, so we used the earlier transistors, then it came as IC technology, and somewhere where using the transistor number per chip, you see it has grown, in a straight way. We are using now Core i7, even though quad-core processors we have left behind. We are soon going to probably leave Core i7 also, because this computer still has a storage issue, it has the performance issue. So where we are working on quantum computers, where as a single chip component gets closer to that of individual atoms. We are working simply as in the nanoscale, where we are trying to work as a single memory chips, single electron memory chips. We are trying to use as now the information storage which earlier we used as a 0 and 1 in classical bits, now in qubits. When we are talking about in qubit, it's in a computing, quantum computing, a qubit or a quantum bit is the basic unit of quantum information, the quantum version of the classical binary system of 0 and 1. A qubit can be made from simply by trapping an ion, or by working on a neutral atom, or it can be a quantum dot. Even though if we are working in the previous generation of computer, where we were working on silicon memory by doping, by inserting phosphorus like pentavalent, so that too can be used as qubit through a different mechanism. And also further we can use NV centers in diamonds, and moreover the latest one, that is the superconducting circuits, where using the Josephson junctions, and by insulating two junctions with some insulating layer and acting as a capacitor, storage capacitor, it acts as a capacitor. So that quantum computing circuits are being used as qubits in the recent times. So if you see in the qubits, so how the IBM or the present way we have increased the qubit number. So 1998, 2 qubits, IBM, Oxford, MIT 1998, they were able to fabricate, but now 120 qubits. So it's a classical version of, as I said, is a classical version of the 0 and 1 with the bit information we are using, but the space is shrinking. The information is being used to be stored in these qubits, much higher space. So giving this idea, this is all about the computers. Where we are working on 2 aspects of the computers. One is the memory storage, second is the processor. One of the processor where we are having an issue is the random access memory. Random access memory is a device where we are, for example, we are writing something on the computer or the laptop, we are writing it in the form of an electrical information. That electrical information goes to the computer, and in the motherboard, the information is being retained or stored as magnetic information or magnetic bits. So in short, we can say we are writing electrically, the information is getting stored as magnetically. So random access memory devices help in this category. They come in 2 categories. One is volatile and another is non-volatile. When we are talking about volatile, it means once the power is plugged in, the information is there. When the power goes off, the electrical pulse goes off, the computer goes off, so information is lost. It is a volatile memory. It's a volatile information. It has gone. Now we are trying to work in a non-volatile memory. Even though the light has not gone, the electrical signal has gone, the light has gone, electrical information, or you can say the electrical current has gone, the information is still in contact. That means computer is not working, the screen is not working. Once the light turns on, you start your computer, it will show you the information therein where you left. So that's where we are working as non-volatile memories, and which is right now the current focus of the researchers. Talking about these information of the computers, where we started as the RAM. So RAM starts from the ferroelectric materials. Among the ferroelectric materials, they are dielectric ionic crystals which exhibit spontaneous polarization. They have very good, they show, in fact, I may call, as you polarize them, they show good piezoelectric and pyroelectric factors also. However, I'm going to talk about a very one particular piezoelectric material, which is the main material largely talked about by the researchers. Okay, let's first of all, before we move to there, let's talk about how the ferroelectric materials are working. It is just simply as the magnetic materials are working. They are randomly oriented before you apply any electric field. Once you apply an electric field, they start getting polarized in one direction. So that's how we get a similar kind of a MH loop. We get here a PE loop. It has saturation polarization, remnant polarization, and corrosive field. All that information where we have a similar kind in magnetic versus the magnetic BMH loop. So the ferroelectric material, it exists actually in 2 or more states with a non-zero polarization in an absence of an electric field if it is a ferroelectric. It has a hysteresis loop, as I showed it, polarization up and polarization down. It has a double well energy. The basic one, the most important one, is the barium titanate, which is a prototype of ferroelectric material. Is the structure is like this, cationics A and cationic B, you can see, and with the main simple unit cell with 5 atoms per unit cell. And what happens as we play with the temperature? The temperature is an important aspect in barium titanium oxide. As of high temperature, if we discuss, it's a cubic paraelectric. When we talk about 130 degrees centigrade, it is tetragonal. 5 degree it's orthogonal rhombic, and 90 degree it's rhombohedral. So you see it is changing with the change of temperature, it is changing the structure. The purpose of our work is to fabricate nanocrystals of the magnetic metals or metal oxides as recording media, as components to miniaturize electronic devices, as sensors, as ferrofluids, as labeling the agents for carriers in biology, and diagnostic and therapeutic tools in medicine. I'm hearing some noises. Can you, somebody stop that? So let me go to, this is the work which we have done in this case of ferroelectric materials. We started basically not with barium titanate, we started with the bismuth. So we doped bismuth with Nd. It's a very good material, Nd. If you dope it with barium titanate or bismuth titanate or any other material, it actually increases the polarization in a material. So it helps us in increasing the ferroelectric character of a material. So looking into this aspect, we prepared a material. We see the nanoparticles prepared are almost spherical in size. They were having only in the composition of 5% some impurity phases, unwanted unfortunately, but they were there. We studied the dielectric constant. It was not as high, but it was okay, but the dielectric loss was less. However, when we studied the polarization versus electric field, which is the requirement of a ferroelectric material in order to be used as a RAM, it was not that good. It was very, very low, and it was in elliptical, almost elliptical shaped, not that S-loop shaped which we need. So we studied again, not here with bismuth, we studied with barium using the same mechanism. What we got a very high dielectric constant, we got a low dielectric loss, the polarization increased for 5% and then decreased as we moved to 20% doping. The polarization versus electric field, however, was again elliptical. It was not S-type. What we got was very low in the powder material. Here we did a one thing. We used this powder material as a target. We deposit this material in the form of film using the PLD technique, and on the silicon substrate we got the PE with a higher value of almost 140. But again, the problem of that it has not the it is not S type, which is the saturation one, or MS type or PE type exactly required. What we did, we changed a further experiment by using the swift heavy ion irradiation. It's a very good technique in order to create the defects or the damages in a material in a controlled fashion, which helps to change the structure, which helps us to tune the properties of the material. So using this technique, one must remember that we need to use two things. One, the radiation can be very damaging if it has is not been worked properly. So a previous data is required, a previous experience is required, how to calculate how much damages are to be made, how much energy is to be embedded, how much target energy is required, how much stopping energy is required. That calculation should be done. So here is the stopping energy or the nuclear energy stopping or the electronic energy loss. Those needs to be calculated before moving ahead for any kind of nuclear interaction or ion implantation or damage what we are talking about. And the damages could be, it could be the point defects, it could be the columnar defects, it could be a cluster of the defects. These three can be there. So what we did, we irradiated the film with 150 mega electron volt using the IUC facility at New Delhi. So we scanned it for 10 minutes, 1 centimeter square, with a flux of 3 into 10 to the power 15. A gold ion beam was used. So the SEM, you can see the SEM shows the line or a scratch It's almost a kind of a column defect there. So atomic folds shows there is a roughness. Scratches are there in the film, which are or showing the film is very, very rough. So as we moved to study the PE measurement for the films, we saw it has now come to somewhere in a S type. What was we looking actually? So we believe that we have somehow been successful and we have increased the PE value. We have got the PE almost around 109 for x is equal to 0.1. That means almost 10%, and as it increased that from 15%, it has gone more and more higher value was achieved. What we saw further, we tried to hit the bottom of the layer. We tried to hit the bottom of the layer. I mean to say, we tried to hit the substrate, and as the substrate was hitting, there at the same time we used to measure PE again. So the loop was shifting from the negative side to the positive side. That means it was shifting from minus y towards the positive y, and that's an offset polarization effect which we observed in this material, and the offset was much better, higher when it was 200 degrees centigrade. So where from it's coming? It's actually coming from asymmetric leakage current which is being generated as we heat the bottom of the substrate. So this shows that our samples, our material can be a good application of RAM in high temperature. When it's at a high temperature, where the temperature, the temperature effect is there, they act as a depolarizing, or they are acting as distorting elements to cancel the polarization effects. However, this material was self-reliant and good to show that the properties are better to a certain extent. So next one is the multi-feroic material, which I am going to talk about. The when we are talking about multi-feroic materials, they are the combination of two or more electric properties. That means they can be, they are having a same material as ferroelectric or ferromagnetic or ferroelasticity could be all together. So it is interjection of the two or three properties in oxide materials, and here we see various types of multi-feroic materials, and the properties are now being studied as a one in together, like it is magnetoelectric or ferroelectric plus ferromagnetism, to understand the multi-feroic behavior of a material, how they can be utilized. In our study, what we did, we used a barium bismuth, this BFO material, multi-feroic material with the co-doping, and you can see the SEM picture showing the very clear crystals of, though its size should not be calculated from the SEM, it should be calculated from the TEM. So here we have done some calculation from the SEM, which are showing in 0.19 micrometer to 0.14 micrometer and 0.23 micron for the three samples. So basically, why we studied this material? We studied this using this material for absorption of the energy, absorption of the radiations, which are usually happening when we are using any electrical device, such as if you are using the iPhone or you are using the Samsung, they are emitting certain radiation, harmful radiation. There is a permissible limit, that beyond that permissible limit, one should not use those devices. So we try to use this material as for application of an absorber. So this is here you can see we try to study the dielectric properties of these materials, and the Dielectric constant showed almost it is 24, touching 24. The Dielectric constant was increasing. It was highest for 15%. Dielectric loss was very, very low. It was less than 1, so that means the bridge can survive. It's a very good material for low loss, and AC conductivity of the material showed that it is good also. However, in the magnetic part, we saw the magnetism of the material is not as high, which is one of the characteristics. Better, it should be higher end, but unfortunately, it was not that much. So what we did, we studied the TE and TM, which is trans electromagnetic and transmagnetic mode of the material, in order to see how this material can be utilized in higher frequency range as absorbing. So absorption shows that this material is having a good absorption up to 2.4 gigahertz. That's the dotted lines, the blue dotted lines you can see in trans electromagnetic mode. We studied this material in another way, how it can be utilized as a good absorption. So the schematic diagram shows 2D structures and 3D structures proposed in order to show that this material can be utilized in the forms or in the materials where we need to absorb the higher frequency, which could be damaging, which could be very harmful to the human body. So here you see we have changed the angular position from 0 degree to 20 degree. So it showed that the absorption is still in contact, and up to 1, you can see 1 means that higher absorption. So up to 6 gigahertz, when we are changing the frequency from 1 to 6 gigahertz, and we are changing the angular position from 0 to 20 degrees, it shows the absorption value is very, very high, almost around 1%. 1 means 100%. It's not fully 100%. It was there 96% in our case. So this is one aspect of these ferroelectric or multi-feroic material. Another aspect we try to study how they can be used as piezoelectric and piezomagnetic composite materials, so that they can be used as for RAM devices, they can be used as multi-feroic materials, they can be used as non-volatile in cases. What we did in this case, a piezomagnetic, you can see this is a combination of two structures. That's we used cobalt, chromium, iron oxide, and which is a piezomagnetic, and we doped with it with a piezoelectric, that was a barium titanate. Once we started doping, we see the loop structure is changing from 0-0 composition to 1, that's 100%. You can see the loop is shifting. It is becoming more elliptical. It's getting more elongated, and the value is increasing from 3 to 12 almost. So this is getting better multiferroic or piezomagnetic properties as we dope piezoelectric properties, as we dope the piezomagnetic with piezoelectric. We saw the loop here, the magnetic properties, which in our earlier case where we saw the magnetic properties were not better, they were very, very less. But in this case, you can see the loop is saturated, MS loop is saturated, and it is of higher value. And that was one important aspect we found, that how to tune the properties of these materials, how to play with these. So what it just suggests that if you have a right kind of doping, if you have a right kind of a matrix, and you have a right kind of a composition, so then you can tune the properties of these materials and you can miniaturize them, and as per your requirement, as per the design of your experiment. This is another aspect of the magnetic materials, which is the final talk about, which I'm going to talk about. which about the ceramic oxides, how we can utilize them as practically for magnetic properties as storage devices or something as memory switches. What is here the basic thing which is very interesting, we try to anchor the material with the graphene, very good conducting material. We try to use it. Could it help to improve the magnetic properties of material? We saw the ME loop up to MH showing up to 20 EMU per gram. However, when we tried the same material without the graphene, we saw that the magnetic properties are better. So that was that this, it was not helping us the way we thought that could graphene can be used, which is one of the revolutionary materials nowadays. However, we have not stopped it. We are still intact. We're trying to see could the graphene can be used as one of the insulating materials, or it could be used as one of the top or the bottom layers when we are talking about the metal junctions. This is the important experiment which currently is going. We are working on that. We have designed it as multi-junction materials, tunnel junction for high density data storage, where we try to two ways. One, we try to use the material as magnesium oxide as an insulating layer. We use it as a copper as an insulating layer. That's a conducting layer. Copper is again a conducting. Here, magnesium oxide is an insulating in a different way. So we studied the MH loop of this, where the temperature was used as a different one. So however, we saw not too much changes at 250 degrees centigrade post annealing and 400 for post annealing. Almost the switching character was the same. However, we saw when we are doping with the copper, we saw that the percentage of the TMR, that's the magnetoresistance, is changing from 3.31 to 4.12%. And here I would conclude with my talk that the magnetic properties which we basically are discussing here is actually helping us to understand how the materials can be utilized in a different prospects, be it electrical, using as them as a RAMs, where we write as I said electrically and we are reading them magnetically, how we can increase the storage capacity of the materials, how we can utilize the same materials for quantum computing, which is now the quantum computers, the present new generation of the computers. So how we can utilize them, and if there is any question or any comment, I would like to hear it. And I'm thankful to the organizers for giving me a chance to speak, to present in a short time some of my work. Thank you very much.
Thank you, Professor Khalid. Professor Khalid has highlighted on the topic of ceramic oxides, multi-feroic and magnetic properties. He has talked about the history of semiconductors, the history of computers, growth of data, and as the data grows, there is high demand for storage capacity. He talked about the quantum connectivity and quantum computing. He highlighted the concept of qubits. Then he talked about the superconducting circuits.